Now let us take a question. See, here they have given a question that if z is equal to 1 minus iota root 3 upon 1 plus iota root 3, then we have to find the argument of z. Now, first I will go with the basic method where z is given as 1 minus iota root 3 divided by 1 plus iota root 3. So, 1 minus iota root 3, that means we are multiplying the denominator by its conjugate as well as in the numerator. So, this is iota root 3. Now, when we multiply, what we will get? So, just multiply, we are getting 1 minus iota root 3, then minus of iota root 3. This becomes minus minus plus, but due to iota square, it will still become minus. Root 3 into root 3 is 3 whole divided by, we are having, you can see this becomes 1 plus root 3 whole square is just 3. So, we are having minus 2 and this becomes minus of 2 iota root 3 and whole divided by 4. So, now if you just separate them, we will be going to get 1 upon 2 and plus again minus root 3 upon 2 iota. So, here we know that we have to convert this particular complex number into polar form now. Now, to convert this particular format into this particular complex number, which is already we have obtained the Cartesian form of the complex number. Now, let us convert it to the polar form where I want to find only the argument. Now, you can see that the real part, generally we say it as A, which is actually r cos theta, and that is minus of 1 upon 2. In the same way, the imaginary part B, which used to be r sin theta, is given as minus root 3 upon 2. Both are negative. That means we have to take them to the third quadrant. Third quadrant means pi plus. So, we can go with the formula tan theta, that is equal to B upon A. When you put these values, this becomes minus root 3 upon 2 and 1 upon 2 will give you only root 3. And root 3 is for tan 60 degree. As they have asked the answer in terms of degrees, I am not going to convert to pi by 3. I am going to take only 60 degree and we have to go to the third quadrant. Third quadrant means it will be 180 plus 60. That means this will give you the answer as 240. Or on the other side, if you go, this will be, we will be going to take in the third quadrant means minus of 180 minus 60. That means we can also take 120 degrees. So, both are correct. It depends on the span of the angle that you are going to take. Now, here, since we can see that minus 120 is not there, but 240 is given to us. So, this is the answer of this particular question. But now, the short technique. If you want to go for the properties of the conjugates, you can see that we'll be going to get the result much more faster than this particular technique. So, for that, let us convert this particular given complex number, which is z is equal to 1 minus iota root 3 whole divided by 1 plus iota root 3. I want to find the argument of this complex number. So, it is a division of two complex numbers. So, if I go with the first one, here we can see that cos theta is positive, sin theta is negative. Positive and negative. Cos is positive, sin is negative. We are in the fourth quadrant. If we are in the fourth quadrant, tan theta, which is B upon A minus root 3 upon 1, that is giving you minus of root 3. So, here we can convert that this angle is minus of 60 degree. So, we will say that the argument of the numerator is minus 60 degree. When we come to the denominator, what you will get? We are having positive and positive. Again, if I find tan theta for this one, this is only root 3 divided by 1, which will give you tan 60 degree. That means the argument of the denominator is just 60 degree. And we want to find, let this one be represented as Z1 and this one be represented as Z2. So, Z is equal to Z1 upon Z2. We want to find the argument. And as per the property, when we apply that argument of this one, this becomes argument of Z1 minus, because for division we have a minus sign, for multiplication we have plus sign. So, minus argument of Z2. You know that for Z1 we have already calculated it was coming minus of 60 degree. then this is minus of the original angle what we are getting here was only 60 degree. So I'll be going to put 60 degree. So we are having the answer minus 120 degree, or definitely minus 120 degrees like this. So this is minus 120 degree, or you can come from this side, this will be 240. So your answer is still 240 degree. It depends on you that how you are going to do that division format. Either you divide it and then find the argument, or use the property which is much more easier than the original method. Now let's take one more question of the same type. Here they are not asking you the argument. The other name for argument is amplitude. Same as with modulus we have magnitude, for argument we are having here amplitude. We want to find the amplitude of the given complex number. You may get a bit of confusion that how this particular term is been given, but this is as it is, where it is written that 1 plus root 3 iota divided by root 3 plus 1. This one is purely real. This is not going to play any role, because for this can be treated as a constant. Whenever it is just a constant, definitely that constant can be written as k plus 0 iota. That means cos is having some answer, but sine is 0. Here its argument is 0. So we are having a complex number in which this one is z1 and this one is z2. Definitely if I want to find z1 divided by z2, I want to find the argument of this one, that is argument, or I'll write there amplitude. So amplitude of this division will be amplitude of z1 minus amplitude of z2. Since z2 is purely real, it is not having the imaginary parts, its argument is 0 minus, if I go for the numerator, since you can see that here 1 is given and here root 3 is given, and if I just check for 1 plus iota root 3, here cos theta is being given 1, which is r, that is equal to a, and b, which is actually r sin theta, this is given as root 3. We can go with the tan theta, which is just root 3, and this will give you tan of pi by 3, that is 60 degree. So here theta is pi by 3. So 60 degree is given to you. So for the numerator, the argument is just pi by 3. So you have to keep this thing in mind, that whenever we are having purely real terms, the imaginary part is 0. Imaginary part is 0 means argument is 0. So what we are going to say, that here this particular question is having the answer just pi by 3. So let us take the next question, which is again asking you to find the amplitude of the given complex number. Now this is having some twist of trigonometry. So the trigonometry twist here is z is equal to sine alpha plus iota 1 minus cos alpha. And we know that for a polar form, if I just write the polar form, this is a constant, that is r. Then we need to have cos theta plus iota sine theta. Means then only I will say that the argument or the amplitude of this complex number is just theta. Clear? So first we have to convert this one into a standard form. Standard form means the term without iota should be in terms of cos, and the term with iota should have sine. So in that case, I'll be going to apply the formula of trigonometry. That is, here we'll be going to write sine alpha upon 2 cos alpha upon 2 for the first part, and then iota 1 minus cos theta. This is actually 2 sine square theta by 2. Here alpha is given, so alpha by 2. So this is our complex number. Now from here I will be going to take sine alpha by 2 common. If you take sine alpha by 2 common, we are left with cos alpha by 2 plus iota sine alpha by 2. If at all you want to keep it like this, then we know that this part is a plus iota b. That means b is this part. If you want to just check with the basic method, the basic method says that tan theta will be equal to b upon a, which is 2 sine square alpha upon 2 whole divided by 2. We are having sine alpha upon 2 and cos alpha upon 2. You'll be going to see that this will get cancelled. This is giving you only tan alpha by 2. Then we'll say that theta is alpha by 2. Now that is one method. The other method is, we know that a constant is being taken common and it is already written in the polar form. So the argument, or we'll say amplitude of Z will be just alpha by 2. So this is a very simple question. It depends on you that how you are going to apply. You can go with the basic method also, or you can apply the short techniques. Now there is, apart from your Cartesian form of complex number, polar form of a complex number, there is one more form that is known as exponential form of complex number. It is also known as Euler's form of complex number, where a complex number which till now we have studied as Z is equal to a plus iota b is written in the polar form as r cos theta plus iota sin theta, and in this particular form we are going to write this one as Z is equal to r will be as it is, that is the modulus, and e to the power iota theta. Just we have to check that argument. That argument will be written to the power of e with iota. So this is the Euler's form where exponential is being used, and this will give you much more shorter form of a complex number. I'll take one example here. If we are having a complex number, say for example Z is equal to root 3 minus say iota. If that is the question given to you, where we have to find the Euler's form, or we can say first I'll go to the polar form so that we can have a thorough revision of that one. Here you will see that A is r cos theta, which is actually equal to root 3, and B, which is r sin theta, is equal to minus of 1. We are getting cos as positive, sin as negative. So which quadrant? It is the fourth quadrant. So fourth quadrant means I'll be going to first find r, which is root of 3 plus 1. That will give you only 2. And if I go with the other formula where the tan theta has been taken, b upon a means minus 1 upon root 3. This is 30 degree, or we can say pi by 6. I'll just take 30 degree here. So this is having a negative sign, so I'll be going to put pi by 6, or we can take 30 degree also. So I'm putting pi by 6, and we are taking in the fourth quadrant. So in the fourth quadrant means this is tan of minus pi by 6. So we are having the argument as minus pi by 6. If anyone asks you to find the polar form, we know how to write Z is equal to 2 cos minus pi by 6 plus iota sin minus pi by 6. And the question which I have just explained to you, that is where we want to find the exponential form or the Euler's form, that will be written as Z is equal to r e to the power iota minus pi by 6. So this is the expansion of this particular complex number. This was in the Cartesian form. We have obtained the polar form, and simultaneously we have written the exponential form also. So this form is easier, shorter, because we know that we are going to write only the modulus r and the argument or the amplitude in the power of e. So this is how we represent a complex number into Euler's form or exponential form. Let's take one more theorem which is there in complex number, but unfortunately the questions will not be going to come for these examinations for which we are studying. But this theorem is very important for you. That is, De Moivre's theorem says that is basically it is dealing with multiplying a complex number n times, or just finding the nth power or finding the nth root. So this theorem has played a role in that. The first and most important thing here is, if n is any rational number, first of all I am taking just a positive number, then cos theta plus iota sin theta, that is taking the polar form. If we are taking a polar form, that means if Z is given as r cos theta plus iota sin theta, and I want to find Z to the power 4, or I want to find to the power 40, or we want to find something else, then how to do? Because it is very difficult for us to multiply a complex number n times. So this theorem has given us a technique, a short technique, where when we go for power n, this n will be going to multiply with the argument only. So that can be obtained by continuously multiplying a complex number with 2, or we can go with 3 complex number also. So when we go for the product, let me tell you that when we take, say, cos theta plus iota sin theta, it is being multiplied by another complex number. Let us take cos alpha and iota sin alpha. What will happen if the two complex numbers are multiplied? If you multiplied them, so we'll be going to see this will give you cos theta cos alpha. Then we have, again it will be multiplying, and we'll be going to get the term as plus iota sin theta and cos alpha. Then taking with this particular term, so we are having cos theta, that is this one, with iota sin alpha, and at last iota and iota is giving you minus 1. So this is having iota, and this term is going to give you minus, and this is sin theta and sin alpha. You'll be going to see that the term without the iota, that is the real part, will be going to have cos A cos B minus sin A sin B. So this is a formula of cos A plus B. So this can be written as cos A plus B, means cos theta plus alpha. And when we go for the other one, when we take iota common, we are having a formula sin A cos B plus cos A sin B. So this is a formula of sin A plus B, means sin theta plus alpha. So what you can see, when two complex numbers are multiplied, then the arguments get added. If we are multiplying it 3 times, so we will be going to have sum of all the 3 amplitudes or the arguments. In the same way, when all the complex numbers are same, that is why this result has been derived. That means when we are going to multiply, if all this theta 1, theta 2, theta 3, they all are theta, you will be going to get n theta. So that's what the theorem says, that is, if we are having cos theta plus iota sin theta whole to the power n, then this will be cos of n theta plus iota of sin n theta. This is not only for positive value, it is also for negative value, it is also for fractions. So that is why it is written that if n is any rational number. So what we have to keep it in mind, that whenever we are doing simple power of a complex number, that argument will be multiplied by the power. And in the same way, when we are having the product, so if we go with the product is again when we are multiplying 1, 2, 3 or n number of complex numbers, we'll be going to have the argument as sum of all the arguments of those complex numbers. And in the same way, with the help of these two results, they have derived a formula for finding the nth root also, which says z to the power 1 upon n, because z to the power 1 upon n is the nth root of z. So that is being given as r to the power 1 upon n cos 2 pi k plus theta upon n, where k is having the values 1 less than the index that we are using, because here we are finding, say for example, if we are finding cube root, n will be 3. If n is equal to 3, then k will have the values 0, 1 and 2. That gives the indication cube roots are always 3. When we go for square roots, there are 2. When we go for fourth root, we are having 4. So this is how this particular theorem can be used for finding different powers of n or finding the nth root of a complex number. Let's take a question dealing with that theorem which we have studied just now. Now here we are having division. So as we know that division means the denominator will be going to get a negative power when it is being taken to the numerator. So first of all, we should convert this particular complex number, which is cos alpha plus iota sin alpha, which is already in the form of a polar, that is in polar coordinate system or the polar form. The denominator is not in the polar form because this iota should be there with sign. So what I am going to do, I'll be going to take that iota common here. So definitely we can write this one as cos beta and minus iota sin beta, and we are having whole power 5. So as we can see, I'm not going to apply the theorem, but I'm just simplifying this part. We'll be going to have 4 in the numerator, and in the denominator we are having iota to the power 5, and this one is in the polar form where cos is having plus sign, sin is having a minus sign. So take that minus inside. So this will be cos of minus beta plus iota sine of minus beta. Now, as per the theorem, if I apply the theorem, that is the first statement of the theorem, this 4 will multiply by the argument. So, this becomes cos of 4 alpha iota sine of 4 alpha. In the denominator, we are having cos of minus 5 beta iota sine minus 5 beta. Then this is only iota. So, now we have to take it to the numerator. When this denominator will go to the numerator, we'll get a minus power. So, minus power means that you have to keep it in mind whenever we are multiplying the complex number, add the arguments. When we are dividing the complex number, subtract the arguments. So, that means when we take it to the numerator, this can be written as 4 alpha minus of minus beta will become 5 beta iota sine. Again, that minus beta or minus 5 beta goes to the numerator. It is minus of 5 beta will be plus 5 beta. Now, this is there. Now, this can be again simplified by multiplying iota in the numerator and denominator. This becomes iota with a minus sign. So, when you multiply this part, then we will be going to get, definitely when we shift this minus inside, we will be going to have minus iota cos 4 alpha plus 5 beta. This iota is minus and minus becoming plus. So, sine of 4 alpha plus 5 beta. So, clearly we can see the answer that we are getting is the C part, which is sine 4 alpha plus 5 beta minus iota cos 4 alpha plus 5 beta. Just you have to keep few things in mind. Whenever we are applying this theorem, we should have the polar form. Now, let us take one simple use of the theorem where we found the formula for finding the nth root. That formula was z to the power 1 upon n was r to the power 1 upon n cos 2 pi k plus theta upon n iota sine 2 pi k plus theta upon n. Now, here we are finding cube root, means n is equal to 3. So, the formula says z to the power 1 upon 3 is r to the power 1 upon 3 and cos. So, when we take n is equal to 3, definitely the value of k will be 0, 1 and 2. So, that will become 2 pi k, I am just putting that k as it is, plus theta, okay, done, whole divided by 3 and iota sine 2 pi k plus theta divided by 3. This will be the formula for finding the cube root, and we are here doing cube root of unity. Unity means I am going to find for 1. If you want to apply the theorem, first we will be going to write this one as 1 plus 0 iota. This is giving you r is equal to 1 and theta, definitely we are having cos term but we are not having sine term. So, theta is 0 degree. Put these values, you will get the results, that is first will be cos 0 plus iota sine 0 whole to the power 1 upon 3. That is what we want to find. And here value of k is 0, 1, 2, 3 and here theta, as we can say theta is 0. So, this part will go. Here I will be going to put 0. So, we are going to get only 2 pi k divided by 3. And if you just put those values, so first if I take k is equal to 0, if k is equal to 0, the first answer that we will get as 1. If I put k is equal to 1, this becomes 2 pi by 3. So, the second value will be having 2 pi by 3. Third one, when you put k is equal to 2, this becomes 4. So, the third one is this one. So, if you just convert this one, because the Euler's form can be written like this, you can see it very well. Now, if I just write the values, you will be going to see the answer will be 1. Simplify this part, this term, this will be minus 1 upon 2 plus iota root 3 upon 2. And the third one, since 4 pi by 3 is in the fourth quadrant, so this will be minus 1 upon 2 minus iota root 3 upon 2. So, we have 1, we have this term and we have this term. This can also be obtained if you don't want to apply that particular theorem. So what we can do for this, suppose we want to find the cube root of 1. Let that cube root be x. So we are having x cube equal to 1. This can be written as x cube minus 1 is equal to 0. So we are having x minus 1. We are having x square plus x plus 1. So this will give you one answer from this one, and the other one is a quadratic equation in which roots are not real. If you just find that value, this is minus b plus or minus iota root 3, or just I'll put square root of b square minus 4ac upon 2a. So this will also give you the same result, because this can be written as x minus 1 plus, so 1 minus 4 is minus of 3. That will give you iota root 3 divided by 2. So it depends on us. If you want to use the factorization method, then also it is okay. Otherwise, you can use the particular theorem to get the cube roots of unity. So cube root of unity is 1 minus 1 plus iota root 3 upon 2 minus 1 minus iota root 3 upon 2. This is having a very beautiful property of especially the cube root of ones. So let us take that part. And as we have just studied about the cube root of unity, from which we derived that 1 and minus 1 plus iota root 3 whole divided by 2 minus 1 minus iota root 3 divided by 2. So we'll not be remembering these terms as so big one. Simple Greek letter is being used, which is omega. That is, this one is as it is. If I take this one, this is written as omega, and this is square of the omega. If you want to find, you can also prove it that the third value is actually square of the first value. So these are the three important cube roots of unity, which is having very beautiful property. Rather, it's a property of all type of roots. Whether you are finding cube root, fourth root, fifth root, 10th root, anything, the sum of all the roots is always 0. So this is the first and more very important property, which will be explored by many questions. And definitely, since it is a cube root, if you want to find cube of this number, it will always come 1. And the last one is, when we are having the same format, it is the same concept that we have to remember. Their sum will always be 0 when n is not a multiple of 3. Means if I want to find 1, then omega to the power 4. If I write omega to the power 10, this will always give you 0, because n is not a multiple of 3. But when you are taking n as a multiple of 3, means 1 omega to the power 6, and suppose we are having omega to the power 33, the result will always come 3. Why? Because when we are having cube, this will always convert to 1. This will also convert to 1. So 1 plus 1 plus 1 will give you always 3, and this will always give you 0. So just remember these three properties, rather the first two properties, to solve the questions of complex number dealing with the cube root of unity. Let's take a question which is dealing with the cube root of unity, that is omega. Now this says, now we have to get the value when 1 plus omega minus omega square is multiplied by 1 minus omega and omega square. So I'll be going to take care about the properties. First, we should recall the properties. The properties for omega is 1 plus omega square is always 0. That means wherever we see 1 plus omega, I'm going to put minus omega square. And wherever we see 1 plus omega square, we are going to put minus omega. So I have derived these two things from the given important property of the cube root of unity. Now the question says 1 plus omega minus omega square and 1 minus omega plus omega square. So we can see that these are the positive terms. So in place of 1 plus omega, I can put minus of omega square. And here this becomes minus of omega with minus of omega. So we are having minus 2 omega square multiplied by minus 2 omega. So this minus minus getting cancelled, 2 2s are 4, and we are having omega cube, and omega cube is definitely 1. So our answer is 4. It's a very simple question. So we are having a question here that we have to find the value, that is the value of a plus b omega plus omega square divided by b plus c omega plus a omega square plus then a plus b omega plus c omega square divided by c plus a omega plus b omega square will be. Now to get this one, I'll be going to take care about very simple thing that we know that omega cube is always 1. If that concept we can take, and apart from that 1 plus omega square, later on we'll be going to use this property also. Now if you see the first part, this is a plus b omega plus c omega square whole divided by b plus c omega plus a omega square. Now if you want to just cancel this numerator and denominator, we should have a free in the denominator. So I'll be going to take omega square from the denominator. There can be many methods, but one simple method I am explaining here. Here we are having 1. So first let us write this one as a plus b omega plus c omega square whole divided by 1. This b is having 1, I am putting omega cube. Then c, we can write this one as omega to the power 4, and this is a omega square. So we can have omega square common in the denominator, which will give you b omega c omega square and a. In the numerator we were having a plus b omega plus c omega square. You can see that this part will get cancelled. We are having omega square, so I am giving omega and omega in the numerator and denominator. So we are having omega and omega square in the denominator, which will be omega square. Okay, so this becomes omega upon 1. So this is one method, that is this part is becoming only omega. The other part what we can do here is omega cube. So this one is omega cube. So what we can see that here, if I just convert the numerator, again the same format can be obtained. And if I go with the second part says a plus b omega plus c omega square. In the denominator what I'm going to write, I'll be going to write this one as, we want to have a free, so I'll be going to write c plus a omega. So this is having only 1, so I'm going to write c omega square, omega cube, then a omega, then b omega square. We can write this one as omega to the power 5, or just write omega square. If you take omega common from the denominator, we are having c omega square, a and b omega. In the numerator we were having a plus b omega plus c omega square. So this is getting cancelled. We can simplify. This will be going to have omega square and square in the numerator. So in the numerator we are having omega square and omega cube in the denominator, which will give you only omega. So omega square rather. So what is the sum of these two things? So the sum here, as we can derive from this, it will be minus of 1. So your answer is B. Now let's take a question which is again dealing with the cube root of unity, and here this time we have to find the value of 1 minus omega, 1 minus omega square, and 1 minus omega to the power 4, and 1 minus omega to the power 8. So this is what they are asking you to find. Now here we know that the property that we have is 1 plus omega square will give you 0, and omega cube is always equal to 1. So we'll be going to keep this thing here so that we can apply it. Now we know that when omega cube is given, it is 1. That means every omega which is having a multiple of 3 as its power, we will be going to put it equal to 1. So let me express this one as 1 plus omega. So dear student, this is 1 minus omega square as it is. How to break omega 4, omega to the power 4? This is omega cube into omega by applying the laws of exponent. This will be 1 minus omega to the power 6 into omega square, isn't it? So now omega cube is 1, that means every multiple of 3 in the power will give you 1. So this is 1 minus omega square, 1 minus 1 into omega. I'll be going to write this one, and this is omega square. Now these are again in the repeated form, so I'll be going to write 1 minus omega and 1 minus omega square. So I'll be going to take it as a whole square. Now if you multiply this thing, it will be 1 minus omega square minus omega minus plus omega cube whole to the power 2. Again, now you can see that 1 minus is common, omega plus omega square, and of course this omega cube is 1 whole square. Now how we can write this omega plus omega square will be equal to minus 1. So I'll be going to put this one as 1 minus of minus 1 plus 1. This is whole square. So this becomes 1 plus 1 plus 1. This is 3 whole square. So 3 whole square means 9. So here for this particular question, your answer is 9. Now we are having one more question in the same format, but here the determinant is being used. Now this is if omega is the cube root of unity, then the root of the equation which is given in the form of determinant is. So that's what we have to calculate here. So first I'll be going to do the simplification, because we know we are having a very important property which we are applying for every question dealing with the omega, that this sum is always equal to 0. Now we are having this sum. So as we can see that here, if I go with this particular question, we are having this determinant with us. So I'll be going to take the determinant as x plus 1 omega square, and again omega, x plus omega square, and 1 omega square, 1 and x plus omega. So as we can see that we are having this 1 omega and omega square in all these rows or columns, you can say. Now if I apply a property, that is, to column number 1, I am going to add column 1, column 2 and column 3. Let's add all the columns. So what you will get, we'll be going to get x plus 1 plus omega square, and omega square. Next one is again omega plus x plus omega square plus 1. This is again x plus omega square and 1. And again this becomes omega square 1, and the last one also plus x and omega. So this is 1 and x plus omega. So what we are having here is clear. Now we'll be going to see that 1 omega square 1, omega square 1 and omega, all are available. So their sum is always equal to 0. So this determinant will be going to have x plus 0, x plus 0, x plus 0. Along with that, omega square, x plus omega square and 1, and 1 x plus omega. So now you can take, since we are having all the column, that is all the elements in the column are x, we can take that x common, and we are left with 1 omega x plus omega square 1, omega square 1 and x plus omega. Now we know this is equal to 0, we know it very well. Now I will be going to convert the two elements as 0, which we know that how to do that one. So for that I will be going to do, to row number 2 subtract row number 1, and to row number 3 I am going to subtract row number 1. So what we will be going to have, it's very simple now. X is already there outside, so we are having 1 omega and omega square was there in the first row. When you subtract, this will become 0. When you subtract, this becomes x plus omega square minus omega. Then if you subtract 1 minus omega square, again if you subtract 0, this becomes 1 minus omega, and this becomes x plus omega minus of omega square. Now simply opening the determinant or expanding along column number 1, will be going to have x and multiply the 2. We are having x plus omega square minus omega multiply by x plus omega minus omega square, and these two will multiply, which is 1 minus omega and 1 minus omega square. So let's take care about this thing. This will be x. Now if you multiply, you will be going to get 1x square. Along with that, this x will multiply with this omega minus omega square, and this whole term, I'll be going to take this one as a whole, will multiply with this one. So it is x into omega square minus omega, and at last when you multiply by this thing, you will be going to get this whole term will multiply. They are the same, so I'll be going to get a minus sign, and we are having omega minus omega square whole square. So this is what we are having when minus. Okay, now multiply the rest one. So rest will be 1. We are having plus omega square plus omega, and we are having minus minus plus and minus is there, so minus omega cube. Now this is what we are having. So we'll be simplifying this thing. So for that I need some space. So I'll be going to take the space from this particular point. Now we can expand this one and we'll be going to get x and x square. Then along with that you can take this x common. If this x is common, what is left? So we are having omega minus omega square plus omega square minus of omega, which will cancel. Clear? And the next part we are having whole square of this one. So if you just open the whole square, we'll be going to have omega square minus, that becomes plus 2 times omega cube. Then we are having again with the minus sign, this becomes omega square whole square, means omega to the power 4. And then the next one, if you see, this is minus 1. This one, omega plus omega square. As we know the property, omega plus omega square will be taken as minus 1. So I'll put minus 1. And the last one is minus 1. So this is the term. So first I'll be going to simplify this one. So we'll be going to have x and x square. This will go. There is no term of x now. Now the leftover term that we are having is minus of omega square. This becomes plus of 2. This becomes only omega, because omega to the power 4 is omega cube into omega. So I'm going to have this omega as it is, and this is minus of 3. This overall result, we know that it is equal to 0. I'll put it equal to 0. So if I put it equal to 0, this is x square. Then this term will become minus omega square minus of omega. You can see that minus omega square will give you 1. So we are having here, in place of this, I'll be going to have plus 1, and then this is 2, this is minus 3. Dear student, it is actually becoming x square only. So one answer we are getting, which is x equal to 0. So there is only one answer for this, that is x equal to 0. Neither we are having 1, nor we are having omega, and nor we are having omega square. So for this particular answer we are having, for this particular question, the answer is x equal to 0. That we could have done earlier also. So this is one basic method which I just taught you, and there will be some alternate method. So for that, if I go with that alternate method, you see, now if you take this question, as we are having different values are given to you, if I go with 1, so if you put 1 over there, we know that we have to add them. So 1 omega square, omega square and 1, omega square 1 and omega. So this is giving you a clear indication that if I put x is equal to 1, here I'll be going to get 2. If I put is equal to omega, I'll be going to get 1 plus omega. So here we'll be going to get 2 omega. And if I going to put omega square, at some point I'll be going to get 2 omega square. So there is only one value, that is if I put x is equal to 0, I'll be going to get 1 omega square, omega square and 1, omega square 1 and omega. When you add them all, definitely the property that we have applied just now in this question, where either you go with R1 equal to R1 plus R2 plus R3, you'll be going to see all the things will get added to the numerator, which will give you 1 plus omega square. Next, omega plus omega square plus 1, and next omega square plus 1 plus omega. That means the numerator, the first row will become 0. If first row becomes 0, the result is 0. So determinant will be going to have the answer 0. So that is the second alternate method that we can go with this particular format. When the values are given, put those values in the determinant. Whatever value you are getting, the answer as 0 is your answer. So here for this particular question, this is the second method that we can go for this particular question, where the answer is coming 0.